want to see that all of this study, where will it lead us? Will it help us in the design or not? And as I mentioned earlier, that finally all of those equations we can plot and then check the design through these interaction curves, and we say, okay, for example, if I know the axial load, I can go to this curve and come down and calculate the moment capacity. And then we can say, okay, my moment is okay or not. If the moment is, combination is here, we are safe. Combination is here, is unsafe. So one time we can draw the interaction curve, and then we can check all the loading. Because normally these loading cases in one column, what do you think in a typical bridge pier? How many combinations of PM and M might be there? Actually, there can be 10,000, 15,000 no problem, cases of loading on a single column or a pier that you have to check and make sure that all 10,000, 20,000, whatever number is, that kind of number is, all of them are okay. And you cannot take the maximum or minimum out of them because it doesn't work that way. So we have to check all of them. Now you might ask me, how can you end up with 10,000, 5,000 or some number? Ask me.
Yes, my question is.
Okay, your question. The problem is that we are dealing with earthquakes, dynamic loading, and it's changing all the time. In a typical earthquake, which is this lasts for 30 seconds, we have about 3,000 variations of the loading. So for every variation, you get one loading. So 3,000 values during an earthquake of changing moment and load. One earthquake. Then you need to combine it with other load combinations, with different ways of plus dead load, negative dead load, that dead load, with live load, without live load. You end up with 10 to 20,000 easily. 10,000 you can end up. And then if it's nonlinear case, then every time step has to be 100 nonlinear steps. So 30,000, there you go. So we are dealing with a very large number of loading conditions. So generating the capacity curve one time is very, very, very helpful because that does not change. Only the loading changes. So we keep checking each case, okay. 4,000 times, okay. 1 out of 4,000 not okay, column fails. Right? Because it must satisfy all of them, not some of them, not 90% of them, every one of them. Right? So you have biaxial bending, you have all, this is only uniaxial bending, not even biaxial bending, one moment and one load. We're talking about two direction bending, earthquake can come in any direction, not only in X and Y. Right? And it has two components. So this design of a column actually is a very complicated issue. That's why interaction surface or interaction curve once generated. And now the problem is that this interaction is based on neutral axis angle 0. If there are two moments, one moment is here, moment is here, diagonal moment, we need to first calculate the neutral axis angle, then calculate the capacity on that angle. So neutral axis angle needs to be calculated. That's why the whole surface is needed. So that we can check the capacity anywhere, at any time. Right? So this is how we actually design the column. Okay. This is just to, sorry, go back one. This is just to give you, okay. This is just giving you an idea of how the interaction works on the plant side, right? The ratios here 1 and 1 and 1, and this is normalized way of doing it. That means instead of using the actual values, we divide the P by P max, and we divide the M over M max, and so on and so forth, M over M max, and M P over P max, plus, minus, negative, positive, both direction. So we can normalize it, and then we can calculate the 2 points based on the normalized numbers. Normalized means we divide them to the maximum. Then it becomes non-dimensional. It just becomes a ratio. So it's easy to check what is the ratio directly because it's normalized. Correct? So we can get the capacity the DC ratio from such curves. So you can plot these curves in real numbers, or you can plot them in normalized manner, and then from there we can calculate the capacities. Similarly, This is a case where there is no tension capacity. This is a case with some tension capacity. So if it is a case in which there is no reinforcement, you will get this interaction curve. This portion comes from reinforcement. So if there is no reinforcement, it shifts like this. And more reinforcement, it goes like this. So basically the diagram remains something the same. It just moves up and down, depending upon whether we have reinforcement or not. And more reinforcement, move more down, up. So we know that, okay, relationship of the reinforcement on these curves can be like this. So if you are expecting negative P tension, then you need negative portion of the curve. Otherwise, it won't work, right? And also you can see from here that at this point, then the relationship is such that you may not be able to get the BC ratio that you are looking for. So that's why we need some reinforcement to be able to get some value of the, so basically you need, at zero moment, you still need some capacity, right? So we need some reinforcement to work with that. Otherwise, there may not be any capacity for zero load and zero moment, something. So if there's no NC load, there's no moment capacity. So beam will not work without reinforcement, that's why, because there's no NC load. But if you have some NC load, then some capacity will start to come up, okay? For the moment also. So that is how we try to understand how the moment and load interaction works. If you want more, so this is at some point you will reach maximum moment with about half, let's say, load capacity, right? After you cross that, moment will start to decrease again, right? So that is why we cannot take the maximum P and maximum M and design it. We need to design for all of them because we don't know what the ratio is.
So then we have only tension direct, no moments, only tension in the member.
Of course we can have, why not? You hang something from the column, it would be pure tension.
In the column,
In the column, yes. And you will ask me how. You ask too many questions. It can happen easily, and this is very interesting because many engineers do not realize something which you will learn in the next course, but I'll just tell you, stage construction causes tension in columns. Also, extreme earthquake causes tension in columns because when you bend the building too much, these columns will become in tension.
Extreme columns?
Yes. So there will, there will be tension when you're trying to bend, or too much wind, building is not big enough, so the columns can become in tension. And stage construction loading can also create temporary tension in the columns. But I don't want to go into detail because then we will skip the thing. We will learn about that next time. This is various ways to look at that. Various ways to look at the interaction curve in a little bit more detail. To relate it to the stresses in the reinforcement, to relate it to the stresses in concrete, and so on. And why? You might wonder, why do we need to worry about, because here, if you look at this curve, you can read in your slides more clearly, this portion is governed by compression purely. This portion is governed by compression tension, purely tension. So there are regions in the curve where the strain is such that most of the section will be compression, all the section will be compression, no tension, right? Certain combination of moment and load may not produce any tension because the load is high, moment is also there, but the compression will cancel the tension, so you will have net compression in the section. That is that range over here. So pure compression, combination, tension and then pure tension, something like that. So these regions are very important, and these points normally we calculate these points on the curve, and I will give you an assignment to do that when I give you the work to you, your next assignment. It's a big one, so that's why in 2 weeks I'm not giving you anything. It will be one assignment, so you can take some little bit. Basically, we will calculate these special points. These special points are what? Special points are when there is zero tension or compression on one corner. Other is compression, but other side is zero stress or zero strain. That's it. So that's a special case. When you have no strain on one corner and compression strain 0.003 on one side. That produces a special case of pure compression on the section only, all compression on the section only. Then there is a special case which is here, which has the neutral axis is infinity, all section uniform stress. Just axial load, no moment. So entire section will be uniform strain, uniform stress. That is called P0 case, zero moment case. This calculates that point on the curve. Then another point will be calculated somewhere here, which will correspond to zero tension, zero stress, zero strain on one side, and 003 strain on the other side. So that will be the case after which the section will become in tension. So that is the case, the borderline for compression case. Then another case is when the reinforcement on one side just reach the yield and other side reach 0.003. What is that called? You must know that. Yes. Yes, balance. Balance condition. Balance condition is when the reinforcement has just reached the yield and the strain on the right hand side or left hand side has just reached 0.003 or whatever is the failure. That is the balance point, right? That is the very important point for us because on one side compression will govern, on one side tension will govern, right? So balance point is important to calculate. And then there is a point when the entire, all the reinforcement is yielding tension case, right? So you have all these nice points on the curve which define clear areas. Now why are they important? Splicing. You have reinforcement in the column, one bar is coming here. Of course you cannot have the bar going all 100 stories, right? Every few stories you have to put a lap, a splice. So now if the lap splice is in tension, different rules. If the lap splice is in compression, different rules. So we need to know whether the bar will become in tension or will not come in tension. If it comes in tension, tension splice rules will apply. If it remains in compression, compression splice rules will apply. And tension splice rule means longer splice, more reinforcement is needed. Right? So you need to know these things. But the problem is that 10,000 or 5,000 combination. Some cases compression, some tension, something. So we need to know this case for all of the cases, which is too much. Right? So we calculate the maximum. That's why these points are very important. We need to know where we are so we can check for the corresponding splice length, corresponding crack width and many things. Right? So this curve has a lot of rich information if we know how to use it. And people divide it into these vector lines and then regions are defined and then tension control, this is the compression portion, this is the tension and compression, pure tension. So these are very important and this is a special case of old ACI when 10% of the axial load, beam case, beam line, so this is up to beam line. Beam definition is that the axial load is less than 10%. So if you draw the line at 10%, and you cut here, this becomes your, and the phi factor changes here. The phi is at 0.09 for beams, for columns it is 0.7, right? 6.5 or 7 or 7.5 depending on what dimension. Right? So those things, and here as you can see, phi factor starts to, is different, you get a different curve, and then this is without phi factor, you get another line. Right? That is a cutoff line that you draw, artificial cutoff to prevent compression failure, brittle failure. So even though the capacity calculated is like this, but OR will apply another factor of 0.85 and cut it there, right? Because they don't want you to go too close to pure compression. So all these things we need to see, we can see from these curves. They are very, very rich information there and a lot of things that we can extract if we understand how to use this curve. And how to generate them, you will generate them by yourself. I will ask you to generate those 5 points on the curve for a section that I will give you. You will use the approach that we discussed last time, okay? About step by step dividing it into squares and all the things that we discussed. Okay? So I will send that problem to you by email today when I go back. Alright? You'll get 2 weeks to do that, yeah, to the assignment. Okay, so now we are getting better information on how those equations that we develop can help us to understand many things. This is an effect of symmetry of cross section. I discussed last time a little bit, that when this section is not symmetrical, this is a symmetrical section. Both sides, negative, positive moment, you have the same behavior. If you just put some reinforcement, 4 bars here, 2 bars here, the interaction curve becomes unsymmetrical. It no longer intersects here, this no longer intersects here. It shifts, it rotates, it becomes like that, right? Which means that now you have an inherent eccentricity at those points. So even if the axial load is exactly in the center, you still have moment, because the moment is measured from plastic centroid, not geometric centroid. What is a geometric centroid? If I had a cross section and I cut a paper, cardboard paper of the cross section shape, and I try to put it on my finger, where I will be able to balance that cardboard paper, it will be the geometric centroid, which is the same concept that we're saying, but we don't do that. So it is this point about which the moment of the area is 0. Net moment of the area is 0. That means both direction, the moment of the area is 0. Net. There is no net moment of area. That is that is the definition of the geometric centroid, right? For a square, it is center. Circle also is a center. For a L shape, it is not in the section. It is outside the section. For a C shape, also it's outside the section, right? Now, what is a plastic centroid? Right now, we didn't talk about, when we talk about the geometric shape, we only talk about the geometry. We did not talk about what material it is made from, right? Suppose the section is made of, is like this. We have 4 bars on one side, 2 bars on one side, but the geometric centroid you will calculate to be the same, right? Then, second step is transform cross section. That you take the rebar and convert, because they are 2 different materials, so they are not the same. So we convert the rebar, we multiply it by the modular ratio. You remember modular ratio? The ratio between the modulus of plasticity of steel and concrete. We multiply the area by modular ratio, we put a big area here, then we recalculate the section, geometric centroid. That will become the transformed geometric centroid, right? So that transformed geometric centroid is like a plastic centroid. Which takes into account the difference in the material properties also. So if you put more bars on one side, that centroid will shift, right? So because now, in this case, the center is here, geometric centroid, plastic centroid is a little bit on the left hand side. So now if you apply a load on the center of the section, but the resultant is always on the plastic centroid, so you automatically get a net moment. It means which you get from here. This is the negative, this is the moment. For compression side, this is the moment on the tension side. So if you pull it, you will get it, automatically the section will get a moment. And if you push it, the section will automatically get a moment that you never applied. But it is generated because the section centroid, the capacity of the section and the applied load are not in the same location. So you get this extra moment correction. So that is why unsymmetrical sections have this problem of these plastic centroid not matching with the geometric centroid and then creating this extra problem and shifting the entire interaction surface in a oblong manner. So now it is no longer the same. So now at this point you still have a moment, right? If you want that, you need to have a negative moment to go to that point. You cannot reach the next point anymore, right? So these things are important and they are often not recognized by the simple books and charts because they assume you have 16 bars, 12 bars, 8 bars in section, you don't have 11 bars, which is true. You shouldn't have 11 bars in a column normally. But sometimes we need to do that. As I told you last example of that pile that got cut, I can't do anything. Somebody forgot to put 2 bars in the side. So what do? You have now, instead of 16, you have only 14 bars. So you need to calculate what happened now. So that's why the knowledge of the unsymmetrical reinforcement, unsymmetrical sections and everything is very important, especially when we talk about shear walls later, after midterm. This is the effect of the cross-section shape on the interaction curve. Cross-section shape of the same area, otherwise will interfere with the capacity may be the same, curve will be different, right? This is here, reinforcement like this one, it will be here, another one is here, although they all have almost the same area. This is 18 inch, this is 16 inch, this is 16 inch square, nearly the same area, right? So the area is the same, amount of reinforcement is the same, just the way we put them will shift the interaction curve, moment capacities will change. So this is also interesting to find which is the most efficient one for a particular application. So circle doesn't seem to be the most efficient one, depending upon where the moment direction is. Because circle, the reinforcement, some of the reinforcement is being wasted. If you apply the moment, the reinforcement in the middle is not doing anything. It's on close to neutral axis. It has no stress, so it has no force, so it has no use. Correct? But if you put the reinforcement at the edge, they become more efficient. And this one, you can see from here, most efficient section will be this one. Because all the reinforcement is close to tension and compression, providing you maximum moment capacity. Right? So if you put all of this reinforcement here, nothing. You get nothing. Right? So rebar layout is very important for efficient design. And you can optimize the reinforcement layout if you know the moment direction. But the problem is we do not know the moment direction because there are 4,000, 5,000 moment directions. Right? So circle wins because it will work best in all directions. You don't have to worry about the negative, positive, moment direction. Whatever the moment direction, it still is the same. So it will be fine. That's why people prefer circular columns in bridges and other places, in piles, because they can sustain the moment in all directions with the equal capacity. We don't need to worry about all these complications. This is the effect of reinforcement ratio. So it is very simple, very obvious. You put more reinforcement, parallel lines are generated like this one. Now this is what the books used to do. They will draw curves for you for 1% ratio, 1% reinforcement, 2% reinforcement, 3%, 4%, like that, right? Then you can pick from here how much reinforcement you want by placing your load point P and M. So now you can use this not only for checking the DC ratio, but you can also use this to find out how much reinforcement you need, right? Suppose your point is here, you will provide that reinforcement. If your point is here, you will provide that reinforcement, correct? Next highest one. So that it is never outside the interaction curve. It is outside this curve, it is inside that curve, so you get that reinforcement. So this same curve becomes a design tool. And that's what we learned when we were at your age. All these books. Page number 47, square column that size, 12 bars, DC ratio that much. 16 bars, another page. 18 bars, another page. Right, column size change, another page. So we used to have all these hundreds of thousands of pages for each. And now in software, we do the same thing. When we write the program, we actually do the same thing. We take a section, we generate 8 curves for that section, 8 surfaces for that section inside the program and save them. And whenever we need to design a column, we find out which region it fires after interpolation and we calculate that reinforcement, put it in that location. Right? Now the problem is generating these surfaces takes a long time and people don't like slow software, you know that. You know? Even it's very fast, If it takes more than 2 seconds, you get uneasy. We keep developing these software and helping people, but they always complain and say, oh, this is too slow, right? So then last time we were developing a software, we needed to optimize. So we found a very interesting, neat trick to actually generate only one curve and scale it, which has never been done before. So instead of generating all the surfaces, we found a way to just generate one surface and find the scaling because of this. Because once you generate for one, the compression for that section is known. It doesn't change. It's only the rebar portion that changes. So rebar portion, if you calculate separately, compression column, because of our equation, the way it works, you calculate the capacity of steel separately, 1% steel separately, and concrete separately. Concrete you don't need to scale. Steel you simply scale in this way because you know the pattern and you can just add them together later again without actually having to generate the whole surface. So nothing needs to be done. You just generate one surface and scale it 8 times. And it becomes 8 times faster. Not 2 times faster, 3 times faster, 8 times faster. Suddenly, something that took half an hour takes now a few minutes. So that is how these things can be used. This information can be used to, this is the effect of the reinforcement spacing, how you organize the reinforcement as I mentioned to you. So you can see, just rebar layout can influence the moment capacity. By making the rebar better, you can get more capacity. This cannot change, below that cannot change, because the same amount of reinforcement. But the moment capacity can be increased by changing the pattern of the rebars. So you can tell the contractor next time that I can save some reinforcement for you if you let me rearrange the bars in your column or a shear wall. If you do a little bit more detailed analysis, then you can actually make it more efficient and take out some bars because you can get the same capacity. These are various curves. People have been studying this problem forever. What happens if you change the limiting strain from 0.0035354? Because it's a question, right? We keep talking about what if the strain was not 0.003? What if it is 0.035? What is 0.0034 or something? So of course it's easy. You can just generate these curves and then you can compare them. Okay, this is the way the pattern will change. So not much difference in this area, in the moment side. Why? Simple question. Because moment is controlled by reinforcement, not by concrete. So it doesn't matter what strain you use, right? But here, compression, strain will happen, right? Greater strain, lesser value. Smaller strain, higher value. Why? Because the stress strain curve starts to fall. Do you remember? Concrete stress strain doesn't go up. So if you increase the strain, actually you reduce the stress that you can use. So it doesn't help. That's why they pick up a nice good number of 0.003, which is actually better than 0.0035, right? On that side. So all of these things, and you need to think, you need to see, you need to question, and then you get an idea why people are doing something the way they're doing, and how it affects the final outcome. We have already talked about it. Just to give you another idea, just summarize that this is an interaction surface which looks like an onion, right? And then each line represents one direction of neutral axis. Each point represents one location of neutral axis depth. So by changing the neutral axis direction and the depth, we can generate this surface. Any point which is inside is safe, any point which is outside is unsafe. Right? So we know these things. And these are the equations that we developed. These are actually plots of the same equation. So you can get this equation, you can vary one by one. Every time you vary something, you get 1 point. So you need to define a surface completely, you need infinite number of points. but we don't have infinite number. So typically what we do is we generate 11 points on the curve, minimum 11 to 15 points on the curve. This way 11 to 15 locations of nucleoxide gap, and normally we generate 24 curves in the plan. So that defines the surface. A reasonable one. If the cross section is complicated and cross section is highly unsymmetrical, we probably need to do more. So normally the programs that you will have, they will let you define how many variations and how many variations this way you want to generate the curve, because it's easy for them. So you can generate a very fine surface or a very rough surface, depending upon what is the cross-section type. For circular section, it doesn't matter, you actually don't need a surface. You just need one curve, it's already a surface, because everywhere is the same. Square, you need a few, but for a T section or an L section, you need many, because it's changing all the time. Alright, so now we know why these equations are useful. Some other ways to plot the same information, some other failure surfaces that we normally do not use, but you will find them in the books. Same thing, but you instead of plotting the moments, you start plotting eccentricities. You start plotting 1 over moment, you start plotting that, you start plotting that. You get different surfaces. For example, here we have failure surface of P, Ex and Ey. Rather than plotting the moment, we plot the eccentricity, because that is also sometimes useful to see, so that you get this surface, right? This is a failure surface of half P and Ex and Ey. So we can plot some other surface. So depending upon what the need is, you can plot that same information in different ways, right? And this one is a typical normal surface, P, Mn, and My. This is the normal plot. This is the plot of the eccentricity. This is the plot for the half of the P. So basically, when you see those surfaces, don't get scared. They're just nothing. But moment is converted into E into P, right? So from that P, moment is equal to, E is equal to M divided by P, and then you plot them, right? So you can create these surfaces without much of an issue. These are useful to find out where the maximum eccentricity, if you are not talking about the moment, but rather a load, you want to put the load somewhere, then you know where the load cannot, how far the load can or cannot go directly. This is a way to look at the moment interaction. We have talked about this, positive moment, negative moment, mu, y, and then we plot from there. So just to summarize what we have studied so far, just to let you know various ways that you might encounter. How to check capacity, we have talked about this one. We check the capacity. The problem is that there is no single capacity. There are 3 capacities that you can check. 1, 2, 3, we talked about that, right? So I'm just summarizing it for you again, so you don't forget. This is one method, right? You check the capacity because there is no single capacity for its cross section. There are 3 possible ways. So we define them in this way, this point, and then you define this. This is, some books will give you this one, but this equation only valid for symmetrical, square, or rectangular or square sections, not valid for other shapes. Another method, vector method on the plan for the same constant PU, vector method. This is quite good if the load is not changing, only moment is changing. And this is the most general one, 2pm vector in the 3D space. When we were writing this third one, it seems very logical, but how do you calculate the intersection of a vector with a surface? Not defined, it's not a sphere. Simple problems become very complicated because there is a vector in space of P, M, and there is a surface. How do you calculate the intersection of a surface and a vector? You don't even try. It's not that simple at all. There is no equation, there is no formula, there is no way to do that. So what do? Same thing. You divide the surface into triangles, lots of triangles. and then you check the intersection of each triangle with that arrow. And then if the triangle intersects, okay, fine. So the surface has to be meshed into small, small triangles, and every triangle must be checked somehow, right? And then the problem is that sometimes, this is computers. The problem is there are 4 triangles at one corner, let's say meeting, and the vectors happens to be passing in the point of that intersection of 4 triangles, which is possible. And none of the triangles will say that this point is intersecting me, because it's not. It's on one of those points. So even if you check all the triangles, still it won't work, and many points it will fail because it is falling at intersection of 4 triangles, which no triangle is willing to accept. So you also need to check more checks on lines and every point also to make sure that that doesn't happen. So every point on the vector line. So these simple things become a nightmare for programmers. Load point location, we have talked about this. Just to tell you again, eccentricity, and I understand that, okay, we need to define. So most of these things I showed last time already. I'm just now giving you a little bit more detail so that you can understand them again. And then relationship of that eccentricity with the moment on the section. One question, uniaxial bending and biaxial bending. We talk about a lot, books talk about a lot. People say this is a uniaxial bending, this is a biaxial bending. And today, I told you before, today I can tell you there is no such thing as biaxial bending. Forget about it. It's just a way to look at something. Then, see, biaxial bending means that you're saying that I have a moment about this one, I have a moment about this one, and it's trying to bend the section, right? We call it biaxial bending. But how can you bend the section at the same time about this and this axis? Section is not going to split into 2, and one part of the section goes this way, and one part of the section goes that way. It can't happen. So what will happen? It will go in between somewhere. So the 2 moments will basically create a resultant moment, and the section will bend perpendicular to the resulting moment vector. So it will still bend uniaxially, just the bending axis will change. Only one moment can cause bending, not 2. So we basically are concerned with the resultant moment. We don't care about each moment, really. They are just components of the resultant. So we take the resultant moment and we deal with the resultant moment. So we are actually always dealing with uniaxial bending that way. Just the axis happens to be in a different direction. That's it, right? So this is a case of a symmetrical section and no bending. So you can see from strain will be like this. 0, just pure compression on this one. This is a case where you have eccentricity of load, and then you have a stress strain curve like this. We call it uniaxial bending because the P lies directly on y-axis. So the bending is about x-axis, which is horizontal, correct? But if I move the P here, this angle of bending will change like this, and section will bend like that. That's it. And if I rotate it back, then it becomes a uniaxial bending again. And that's what we do in the computer. We simply rotate the cross section back to horizontal and calculate everything on the horizontal always, rather than trying to calculate everything in that way. So you simply rotate the cross section in such a way that it aligns with the x-axis. So you're always dealing with the same problem, irrespective of the angle. Sometimes this is a biaxial bending in the sense that the point has eccentricity Ex and Ey both. So we call it biaxial bending because now the axis is like this, the section will bend like this. So you have 2 components, My and Mx. In this case, one bar is missing. Even though the load is here, you will still have biaxial bending because plastic centroid is no longer matching with geometric centroid. So even though the applied moment has no eccentricity, section becomes biaxial because of the unsymmetry of the reinforcement and the plastic centroid. So it's not about the loading, it's also about the section. And this is of course a case where you will have complicated biaxial bending because the section is unsymmetrical and also the loading is offset. So both the things will combine together to cause a very, and here the bending axis will be perpendicular to this line. Here, not. Different situation altogether, right? So that's why unsymmetrical sections are very hard to estimate anything about their behavior. So any assumption that we made about unsymmetrical section fails at some point. Okay. What time is it? 25. Okay. Let's conclude this chapter, this topic today. I'm just going to now come back to reality, to ground. We have discussed everything, but do not forget that the original beam things that you learned are still okay, are still valid. They are just a special case of whatever we have learned today. So although we went all the way this way, but basic theory is still there, and that is valid. Only think of it as a special case of the general theory. Don't think of it as a separate theory or a separate process. It is just the same, only some things are simpler. So I just want to summarize this for you, and we can conclude this lecture today. So now we are dealing with a simplified system. Duplexes, cross-section, bars only on one side, no compression bars, very simple. First singly reinforced beam that you people have all studied. Strain diagram we can draw like this. This information will help you to do the assignment because this tells you how these things work. So let's say it's this VS code, we fix the strain 0.0035. From that 0.0035 we draw a line from the duplexes and we can calculate the strain on the steel, center of the steel bars. That comes out to be, in this case, let's say we fix it to be 0.002, right? So what is this condition? Balance condition, right? So we can draw the balance condition by fixing the two strains and drawing them, and wherever they intersect, that becomes our duplexes, correct? So this condition is specially defined, and based on that, then we can put the stress strain curve from VS code on top of that, and from that we can calculate this is 0.87 Fy, including the gamma factor, and that one we calculate from there, and we calculate, we simplify it into the stress block, and then from that you can calculate the moment capacity. So that was the balance condition, and these are the equations that you can use to derive those balance duplexes. Similar, I'm just going back to the actual calculation, so you should not worry. These are all there when we go. But so balance condition is easy because you know the two strain condition. That's perfect. On the same diagram, you can create more conditions that I was talking to you about. ECU 0, right? And ECU very far so that all bars are built in, right? So those are special cases of the same thing. And for each case, you can generate the strain condition and calculate the stresses by setting the conditions for the strain. %% Fy. Sometimes we can say this is strain, this is balance, this is another one as I mentioned here. So you can create as many conditions as possible. This one less than that, this one equal to that, that one less than that. So whatever, half strain, half Fy, 50% that. So from any condition, you can create a corresponding duplexes location and corresponding stress strain, and then use the equation to calculate the capacity. ACI, same thing, calculate the moment, similar way. These are the equations, you people have all seen it. Section, C, Whitney's block, from that point JD, T, compression, a moment of, you can calculate all of these things based on that. So, mu is equal to 0.5 to 0.7. After we calculate the balance condition, the codes say that you cannot use the moment capacity more than mu mb. Why is that? Why they don't want us to use moment more than or equal to balance moment.
Sir, if stress is to 0.0035, we have a brittle failure. So in order to avoid that, we keep it.
Correct. Basically what we want is no compression failure. We want tension failure, so we want to design it for a condition which has a reserve tensile moment capacity. So that will be utilized first before the strain becomes one. In fact, they don't need to worry about this one because the strain 0.003, I mean in any case, in actual condition 0.003 strain never actually comes. Right? It is, but okay, they have developed a system, they need to follow it. So they say, okay, brittle failure we prevent it, which is a good thing. So we cannot put too much reinforcement in the beam, it's not good, especially for earthquake. Too much reinforcement is not good. Doubly reinforced. Where is the second reinforcement here? There should be another reinforcement here. Okay, assume that there are two more bars here. Okay. So area of then steel in compression, steel in tension, total AST is like this one, and these are the equations for that. You have all these in the books. I don't need to repeat them. I'm just telling you that these are special cases of the same thing. In our approach, we don't need to worry about any one of these. Because as many number of bars, we don't care, right? Whatever strain, we don't care. Whatever stress strain, we don't care. All is already included. So basically, the column design program can also be used to design beams. Because just put the P equal to 0 and get that value, and you will be fine. So we don't actually need all of this, except just to follow or satisfy the code requirements. These are some of the limits that they put for flexure in terms of the minimum steel and maximum steel. Why there is a limit on minimum steel? There's a minimum steel limit. There are two limits on minimum steel, or three limits. Yeah. Why there are limits on minimum steel? Why can't, if my moment is very small, why I need to provide, let's say my moment is really small, the architect make big section for me, and the moment I did reinforcement I require was only, let's say, 2 centimeters square from the moment. But the code will tell me put 8 centimeters square there. Why? They do that because in case of overload, the cracking moment capacity is quite large of the section. So, because when you design concrete beams, what is the first assumption? We ignore the concrete tension capacity. We assume that concrete has no tension capacity, which is totally wrong. Concrete has a substantial tension capacity. Let's say your moment is 90. Concrete cracking capacity is 100, right? So, in fact, the reinforcement that you provided for 90 or 80. Let's say your actual moment is 80, but the concrete cracking capacity is 100. So, you provided when you calculated, you ignore the tension capacity. You provided for 80 moment in your reinforcement. Now, let's say there is an overload, live load. What will happen? First of all, the beam will continue to get the moment until it cracks. So, moment will reach 100 and then it will crack. So, reinforcement will not be utilized at that time, so it doesn't matter. Now, when the cracking moment reaches 100, it will crack and suddenly all of the load will go to the rebars, which you haven't designed for 100, you have designed for that one. So, now the rebars will get a lot of load plus an impact, which will be very large. So, the rebars may simply crack, may break, or they rot it too much. So, we say, okay, minimum reinforcement must be related to the cracking moment capacity. So, they have these limits, so that the minimum reinforcement in the beam actually relate to the cracking capacity of the concrete. Wherever you see square root sign with Fc prime under it, be sure this is related to tension capacity, because that is the tension capacity equation. So any equation that you see in the code or anywhere and you see Fc prime, inside and a square root on the outside, be sure this was derived based on the tension capacity of the concrete. And you will see that this equation is also applicable in shear. The shear capacity of concrete is equal to 2 something under root FC prime. So we'll talk about that also. So basically this is related to, you can see from here, the tension capacity multiplied by 6 F by dWt, tension capacity something something, 200 dWt. This is related to temperature. So they have all these limits that they provide for you to make sure that you do not provide reinforcement which is too small. And this happens a lot. A lot of beams get cracked and you cannot understand. Moment is very small and you say everything seems okay, but since the beam is cracking. Reasons are that some people did not follow the minimum limits properly. And sometimes the calculation of the thermal stresses are not done correctly. There are some issues with that. So the minimum reinforcement of the code actually doesn't work. In most of the real buildings, the minimum reinforcement for thermal cracking does not work. It needs to be more than that. Maximum steel, they also put a limit because they want to avoid compression failure. But if you put compression steel, you can go forever. As long as you balance the tension steel with equal compression steel, there is no limit. Because whatever extra compression will come will be taken by the steel, so the concrete is not doing anything. So you can keep on designing infinite. Theoretically speaking, this equation gives you the ability to put infinite reinforcement in a beam. If you balance the tension and compression reinforcement, there is no maximum limit, only practical limit. Right? Deflection will govern, other things will start to govern. But you could design a beam in which you will not be able to put it there, but you may have 1 million square inches here, 1 million square inches here from your calculation, and the code will still say, okay, go ahead. Of course, you can put it there, and there's other things, but theoretically speaking, as long as the compression and tension, because why? Because we allow elastoplastic behavior for steel. Yield goes straight, so we don't care about the failure, because it's just going forever. So, in any case, these limits you need to still follow after we do all of the calculations. Cracking, another issue which is not related to the capacity that we talked about, but section also we need to make sure, in the first lecture I mentioned, check for cracking, deflection and those kind of things. So now we're talking about cracking, right? Cracking is related to this Fs. Fs is equal to something. Working stress method. We go back to limiting the stress, not strain. Now, indirectly limiting the strain, but basically limiting the stress. So we can calculate, there's a factor called W, and this one, and then Z. So I don't want to, because every code has different equations, we don't need to worry about it. What we need to worry about is cracking in beams needs to be avoided. And it depends not only on amount of reinforcement, but more importantly, the distribution of reinforcement. And the Z factor actually is a factor dependent on the distribution of reinforcement. If you just put a lot of reinforcement at one location, a beam, then it will not crack here, but it will crack another location on the same beam, right, on a side. Because the stress, the strain and stresses will redistribute, and then the cracking will move to another location. So we need to provide distributed rebars. So that's why it's the same. That's why good idea is to provide many small bars than few large bars to prevent cracking. But on the other hand, if you provide many small bars, handling cost and other things, our fabrication cost increases. So we have to balance all of those things. But from cracking point of view, more smaller bars are better than few larger bars. So if your cracking does not satisfy, instead of adding bars, just divide them into smaller bars and you will be able to satisfy. Same amount of reinforcement, better distribution will solve the cracking problem. This is the conclusion of the beam section design flowchart, you may call it, right? How do you do the design of a beam for moment, bending moment? We start with a given moment, concrete strength and steel strength and section. That's what you have, correct? Assuming that you have the section, which normally is controlled by the architect. They will tell you, you cannot have a beam more than this one. So they basically govern many sections for you because of the headroom and other clearance. So you have that. Moment will come from analysis, not one moment, hundreds of moments, thousands of moments. Okay, we take one moment. Calculate MRC, calculate the cracking moment, I'm sorry, not cracking moment, moment of resistance of the concrete of the section based on the balance condition, reduced by the factor 0.75 balance, something like that. If MRC is more than MU, that means the capacity of the section, concrete section capacity is already enough. You don't need doubling reinforcement. You go to singly reinforced section design. From that, you calculate the area of steel based on the section, single reinforcement section condition. Check the minimum steel, and then it is okay. You determine the layout of the bars, check the crack width, and then you are okay, right? If not, then you use, if this is, check, if it is, this is less, you use minimum steel, and then you go back to this one here, okay? So minimum steel is employed here. If this is more, moment is more, then you go to W reinforcement beams, you calculate AST, ASC, check AST max, which will always follow, which will never be failed, but you will be okay, you come back to this one. So basically, this diagram, you almost never need to revise the section of the material as long as the layout will be a problem or other things will be a problem, right? But practically, this is how we check. So that is a procedure to follow for the design of the typical beam section. For columns, we have already discussed about that, right? Okay, that's I think is the last slide, and almost is the last minute.